40 light years from Earth, there is a world almost exactly our size, made of rock, sitting in the one place around its star where water could be liquid. Of all the thousands of planets we've found beyond our solar system, this one may be the best bet for life we have ever discovered. Its name is JWST. Right now, the most powerful telescope ever built is staring at it, trying to answer a simple question: does it have air? And the answer is turning out to be one of the hardest things astronomy has ever tried to measure, because the planet's own star keeps getting in the way. This is the story of JWST and the ingenious fight to read a distant Earth. Welcome to the cold beyond. Start with the star. JWST is an ultra-cool red dwarf, a tiny, dim ember of a sun barely bigger than the planet Jupiter, and less than a tenth the mass of our own sun. It's so faint that we only cataloged it properly in this century. But in 2017, astronomers announced something extraordinary. Orbiting this little star are 7 Earth-sized planets, packed in tight, 3 of them in the habitable zone. And the standout is the 4th planet, JWST. It's almost exactly Earth size. Its density says it's rocky like Earth, and it receives roughly the same amount of energy from its star as we get from the sun. On paper, it is the closest thing to a twin of our world that we have ever found in a star's habitable zone. But habitable zone only means liquid water is possible. To be a living world, JWST needs one more thing: an atmosphere. No air, no life as we know it. So that's the question everything now hangs on. Does this distant Earth have an atmosphere? Or is it a bare, airless rock? To find out, you use the same trick we met with K2-ATB. Each time JWST passes in front of its star, a sliver of starlight grazes through any atmosphere on its way to us. Gases in that air absorb specific colors, leaving fingerprints in the light. The James Webb Space Telescope can read those fingerprints. So Webb watched transit after transit, collecting the faint signal. And in 2025, the first detailed results arrived, with a tantalizing hint: a possible trace of methane, a gas that, on Earth, is strongly tied to life. For a moment, it looked like we might be reading the air of a second Earth. But here's where this gets genuinely hard, and where, as always, we pump the brakes. Red dwarfs are violent, blotchy stars. They're covered in giant star spots and bright patches, and they flare constantly. And here's the cruel part: when the light from a spotted, uneven star shines through to your telescope, it can leave fingerprints that look almost exactly like a planet's atmosphere, even when there's nothing there. Astronomers call this stellar contamination, and for planets around red dwarfs, it is the great deceiver. So when the 2025 analysis looked closer, the conclusion was sobering. That hint of methane might not be coming from the planet at all. It could be the star. The same studies did rule some things out. JWST almost certainly doesn't have a thick, hydrogen-rich envelope, and probably not a heavy, Venus-like blanket of carbon dioxide either. But whether it has a thin, Earth-like atmosphere, or no atmosphere at all, remained genuinely open. We had not found air. We had found how hard it is to be sure. So how do you separate the planet from the star? This is where it gets clever. To subtract the star's deception, you need to know exactly what the star's own light looks like without a planet in front of it. And JWST one-handed astronomers gift its innermost planet. JWST 1b is a baked, almost certainly airless rock. When 1b crosses the star, any fingerprint in the light has to be coming from the star itself, not from an atmosphere. So 1b becomes a reference, a way to measure the star's lies so you can subtract them from WE's signal. Through 2026, a major Webb campaign is doing exactly this, gathering more than a dozen additional transits to finally pull the planet's true signal out of the noise. It's one of the most careful measurements ever attempted in astronomy, and the results are landing as we speak. Why go to all this trouble for one planet? Because JWST is a test case for everything that comes next. If Webb confirms a stable atmosphere on a rocky, habitable zone world, it would be the first time in history we've done it, and the gateway to actually searching that air for signs of life. But there's a deeper question hiding here, one that haunts every red dwarf planet. These stars are so violent, with flares far stronger than anything our sun produces, that they may strip the atmospheres off their planets entirely, leaving bare rock in the habitable zone. So, JWST isn't just asking, does this world have air? It's asking something bigger. Can small, angry stars, which are by far the most common stars in the galaxy, hold onto habitable worlds at all? The answer shapes how many places life could even exist. And the remarkable thing is that this isn't a story about the distant future. It's happening now. The observations are being taken. The stars' deceptions are being measured and subtracted. And the verdict on whether JWST holds an atmosphere is expected from this very campaign. It might be the quiet announcement that a distant Earth has air. Or it might be another careful not yet. Another lesson in just how delicate this work is. Either way, we are watching. In real time, humanity learned to do something it has never done before. Read the atmosphere of a world the size of our own, 40 light years away, and tell the planet apart from its star. JWST has been sitting in that red glow for billions of years, keeping it secret. We've finally built the eyes to look. Now we just have to be patient enough and honest enough to believe what they tell us. If you want the honest version of the search for life beyond Earth, the real science behind the headlines, this is the channel for it. This is the cold beyond. The universe is colder, stranger, and closer to an answer than you think. I'll see you in the next one.